Geez. Okay, so 3.5, now finally, we look at the applications of this stuff, exponential growth and decay in particular. Expo growth, and of course, decay. All right, so I've already sort of let the cat out of the bag in class about this stuff. Let's take a look. Okay, so our formula is going to look like the following. F of t equals a sub 0 e to the kt. A sub 0 is going to be your initial population or your initial amount. Okay, so initial amount. K is going to be some sort of growth constant or a, yeah. So let's say this is a growth constant. And if K is less than 0, you're going to have the decay form. And if K is greater than 0, you'll have the growth form. Okay. So decay over here and growth over here. Okay, so let's take a look. Problem 8. You kind of want to have this formula memorized. You'll probably have to see it again in physics and in your chemistry class and you know, your math classes from here on out. They'll be floating about. T in this particular context is the number of years after 2000. And the A in this case is going to be a population in millions. Okay. So first they want you to actually find this model. What do they mean by that? They want you to find what a sub 0 is and what the k value is. How do I do that? Well, they give you information, okay? So they're going to say at time 0, the population is 3.2 million. And then at time 50, the population is 12 million. So in general, at the time, the year 2000, the population 3.2 million. Year 2050, the population is expected to be 12 million. Okay, so you can use that information to solve for the unknown parts of this equation here. In particular, we want to find a sub 0. And we also want to figure out what the heck k is. Once you get those down, you can use your model to make predictions about the population for any given time. Okay. So first, we'll deal with the 0, 3.2. So when you input 0 for t, so this will be our t, you get out the a value. So substitute those into your equation. So you get 3.2 equals a sub 0 times e to the k times 0. Okay. Anything times 0 is 0. So what you're going to see is that this is very simple. A sub 0 is just going to be 3.2 because you'll have e to the 0. E to the 0 is 1. So of course a sub 0 is 3.2 million. So there's 3.2 million people in the year 2000, but I mean, what is that in the context of the formula? That's just the number that goes right here. Okay? So you can kind of look at the coefficient of the exponential term and say, well, that's just your initial population. And we can now rewrite the formula as a equals 3.2 e to the kt. So we've got the first part, this pink part here. Okay. So that's step 1. Step 2, use the other ordered pair to solve for the blue part here, the growth constant. Right? So again, you know, this is your t value, this is your a value, and all you're doing is plugging that information into this formula. Okay, so we'll have a is 12, and then 3.2 e to the k, we don't know, but we know t. So I'm going to write 50k. So I'm just substituting in for t, and then flip-flopping the 50 and the k. So Then we got to solve for k. So in order to solve for k, we have basically an exponential equation. We want to first isolate the exponential term and then use logarithms, natural logs in particular. So first isolate, so I'll divide both sides by 3.2. Okay. Then take natural logs on both sides. So you get ln of e to the 50k equals ln of 12 all over 3.2. ln of e of 50k, well, the cancellation equations tell us that's just going to be 50k. And then over here we have the ln of 12 over 3.2. Finally, solve for k, and I get k is the ln of 12 over 3.2 divided by 50. In general, personally, I don't like to get approximations. I just like to leave it in this form. If you want to get an approximation, that's fine. Go out to, I think, about 4 decimal places, and that'll be okay. But I kind of avoid approximations. It's an error thing. You know, the more approximations you make, the worse the error it becomes. It's like spreading a rumor. You know, when you're only 3 people away from the origin of the rumor, it's still similar to the original rumor, right? But then when you get about 20 people away, the rumor just falls apart, and all of a sudden you don't know what the reality of the situation is or what the original rumor was. Anyways, once we get this formula now, so I can rewrite k with this expression. It looks a bit odd, but you can get used to it. It's a equals a sub 0 e. Oh, so we want to substitute in our values. A equals 3.2 e to the k, which is ln of 12 over 3.2 all over 50 times t. We want to know now in part B, when will the population be 9 million? Okay, so they're saying basically substitute in 9 for A and solve for the time. Okay, so we're going to put 9 here. 3.2 e to the ln of all this mess. 3.2 divided by 50 times t. And then again, we have an exponential equation. You need to solve by first isolating the exponential terms. So I'll divide both sides by 3.2. Then I'm going to take natural logs on both sides. So I'll get natural log of e to the ln of 12 over 3.2 over 50t equals ln of, if you don't like the decimals in your fractions, I don't personally, you can rewrite it as 90 over 32. Just multiply top and bottom by 10. That's perfectly legal. Of course, over here, the ln and the e will cancel each other, so you're left with ln of 12 over 3.2 all over 50 times t equals ln of 90, or well, it's 45 over 16. Just simplifying the fraction. And then you can multiply by reciprocals to get rid of this coefficient here. So 50 all over ln of, and again, I don't like fractions, so I'm going to rewrite this as 120 over 32. And then over here, so you're timesing by 50 all over the ln of 60 all over 16. And then you have t equals 20. You know, you can envision that as that over 1. So it's this times this. So it's not 20, it's 50. Excuse me. 50 ln of 45 over 16 divided by the ln of 30 over 8, which is 15 over 4. Okay. Sorry, my light fell and coffee went everywhere. Sorry about that. So 1 second. I don't have a pause button, unfortunately. So anyways, at this point, go to your calculator and get an approximation for that thing. And, the light, of course, produced a domino effect when it fell. Could not ask for worse results. If I try the planet, I mean, it would take me years to fabricate a similar scenario. But the physics of my reality have produced those effects without my intervention or something, I don't know. Anyways, there's that. We want to evaluate this thing. So I'm just going to get a calculator as well. Just want to make sure. So I did a lot of crazy there simplifications. Let's get the light fixture out of the way here. Okay, so anyways, 50 ln of 45 divided by 16 divided by ln of 15/4. Out of wind because of all that. That's not encouraging. My approximation is 39.1174. So within the 39th year after the year 2000, it'll reach that. So when will the population, it'll be during that year, but you can approximate and say, okay, this is about 40. So in the year 2040, it's going to get to 9 million. So, at the beginning of 2039, it won't be 9 million. So that's why the book is there's the rationale behind 40 instead of 39. Okay. And so maybe I don't want to say approximately. This is not, I'm not rounding here or anything. I'm just saying they want to know the year such that in the beginning of the year, the population is already at 9 million as opposed to the, which year does it eventually reach 9 million. Okay. Let's look at some decay problems. So half-life, we have problem 18. We're dealing with plutonium-239. And this stuff has a half-life of 25,000 years. They tell us initially we have 16 grams of the stuff. And then they ask how many grams are left after a certain period. Okay. So again, we have our formula, A equals A sub 0 e to the kt. And we want to figure out what is A sub 0 and then figure out what is the k value. Okay. All right, so A sub 0 is easy at this point. It's just your initial amount. So A sub 0 must be, where are you? 16 grams. So 16. That'll allow us to rewrite our equation. A equals 16e to the kt. Now we're going to use this half-life information. Okay? So this is a time. They're giving you the time, and they're saying that half the original amount will be left there in this amount of time. So basically at time 25,000, the amount left over is half of the initial amount. So 16 all over 2 will be the A value. So the input of 25,000 leads to an output of 16 over 2. We can write it then as 16 over 2, which is 8. So I'm substituting this information into this formula. So I have 8 equals 16e to the k times t, and t is 25,000, but I don't know k. All right, and this formula is going to allow me to solve for the k value, and then I can use my overall formula to figure out the amount after 25,000 years that will be left over. Okay, so divide both sides by 16. You'll be left with e to the 25,000 k equaling 1/2. Then take the natural log of both sides. So ln of e to the 25,000 k equals ln of 1/2. Then by the cancellation equations, those will go away, just leaving us 25,000 k. Over here, ln of 1/2. And then you could solve for k. It's equal to ln of 1/2 all over 25,000. Okay. So we'll have our growth constant. We put it now into our formula and then answer any question they throw at us. So our formula officially now is A equals 16e to the ln of 1/2 all over 25,000 times t. So in particular, year 25,000, we could do this without a calculator. We could say this is 16e to the ln of 1/2 all over 25,000 times 25,000. Okay. So the 25,000s cancel out, leaving you with 16e to the ln of 1/2. Right. The e and the ln are inverse functions, so the cancellation equations apply there, and you just have 16 times 1/2. In other words, you get 8. So after 25,000 years, you're still going to have 8 grams of this junk laying around. Okay, so the exponential growth formula that we've been playing around with is used a lot in modeling, but it's not very realistic for populations of like humans or animals. And the problem is that this thing grows exponentially. So you don't expect your population to just keep going up and up and up and up and up after a while, right? So you don't expect the human population to just keep growing, because eventually humans will exhaust their resources. So, there's no more food. And I'm not just talking about humans. I mean, imagine 50 leopards in a zoo or something like that, some forest reserve or something, I don't know, and they end up eating all their food. If the population just kept getting bigger and bigger, that would be an issue. So this turns out not to be the ultimate model of the universe. We need to have other exponential equations, and one that we'll see is logistic equation, and that's a good equation because it has a limiting population to it, and it says the population won't exceed a certain amount. Okay, so it's more realistic, and here we go. So logistic growth model, and believe it or not, this model actually comes up when you're doing machine learning. So when you're modeling computer programs off of the way the brain works with firing neurons and stuff like that, they'll use this equation in that context, believe it or not. So there's my little tidbit for the day. Anyways, let's take a look. So 37, they're giving us the logistic equation f of t, which is 100,000, all over 1 plus 5,000 e to the negative t. Okay. So f of t, what does that represent? It's the number of sick people T weeks after the breakout. So you can almost think of it in terms of zombies. So the number of zombies T weeks after the breakout. Okay, so how many zombies do you have at time 0 is the first question. Okay, so what are they asking for? They're asking you to let t equal 0 and find out what f, the number of people that are sick. So f of 0 is 100,000 all over 1 plus 5,000 times e to the negative 0, which is 0. Okay. So e to the 0 is just 1. So you'll have 1 plus 5,000. So you have 100,000 all over 5,001. And we put that in our calculator, approximate it. It's approximately 20 people, or 20 zombies. Okay, part B. How many people are infected at the end of week 4? Okay, so here they're just asking for you to plug 4 into logistic equation. So yeah, f of 4 is 100,000 all over 1 plus 5,000 e to the 4th. Okay, I'm gonna need my calculator for this one. So 100, 100, 1, 2, 3, divided by 1 plus 5,000 times e to the 4th. And yeah, I'm not getting the right number. Oh, I forgot to put a negative sign in there, sorry. Okay, so this is approximately 1,080 people. Then they want to know the limiting size. So this is, the question I was saying before. Eventually, the organism, like the wolves, will eat all of the resources. So eventually, with zombies, everybody's going to be a zombie. So what's the total possible number of zombies out there? And the book is calling that the limiting population. So there can't be more than a certain number of zombies. How do I figure that out? Well, you can put a real huge number in for t. So let t be like 1,000,000 or something like that and see the output. But at the end of the day, it's going to be the numerator. The numerator is going to be your limiting possibility, your limiting population in these problems. So from above, the c value is the limiting population. And other books will use different variables, but that's the idea. Okay. So the limiting population in this case is just the numerator, which is 100,000 people. Right. So you can imagine if the city only has 100,000 people in it, the zombie population is probably not going to. Well, assuming zombies can't reproduce. So there's other issues then, right? So you can imagine rewriting this to reflect the idea that eventually the population will reproduce and replenish itself. And you study that kind of stuff, you take something called differential equations, you'll see that. You'll see it in calculus too as well. Okay. Anyways, Newton's law of cooling is the next kind of equation we have. And a couple of years ago, there was like a real bad winter here in Ohio, and it was so bad you could literally the thing was to take a thing of water and get it boiling and then go outside and throw it up in the air, and it would freeze before it hit the ground. Okay. And so basically what it's saying is that the change in temperature of the liquid is proportional to the difference between the temperature of the liquid and the surrounding temperature. So if there's a real big difference, the rate of change of the temperature is going to be very quick. So if you go outside and you throw boiling water in the air, when it's freezing out, the water's temperature will change very rapidly. Okay? From that formula, you can derive Newton's law of cooling, and Newton's law of cooling is this: T equals C plus T sub 0 minus C times e to the kt. Okay, so we have a bunch of variables that need defining. T is going to be the temperature. C is of the object at time 0. No, sorry, at time t. Okay. T sub 0 is the temperature of the object in the beginning. So in the beginning, in the boiling water example, the temperature of the water was boiling. Okay. So temperature of water or object, whatever it is, at time 0. And then I believe C is the temperature of the surrounding medium. So in the boiling water example, C would have been the temperature outside. Okay, so in the book we have a pizza problem, and you know, if you are ambitious and you're working at your pizza store, you could write up a little computer program to figure out how long exactly your pizza should be, you know, left out before they become kind of inedible or inappropriate to send out on the road. So number 48, we are given some information. The oven temperature is 450 degrees. And this will be the temperature of the pizza when you first take it out of the oven. So in terms of our variables above, that's T sub 0. They give you the room temperature is 70 degrees. And in terms of our variables, that's the surrounding medium. Okay, so that's C. Then they say some information for us to solve for the constant, this K value, this rate. After 5 minutes, we can measure the temperature of the pizza and it'll be 300 degrees. So in the context of what's going on here, what they're giving you is an ordered pair. They're saying at time 5, the temperature of the output is 300. So this input here is little t, and this 300 is the big T. Okay, so first off, we want to use our information to find the unknowns in this formula, and then we can make predictions about how long is it until the temperature of the pizza is, you know, lukewarm or the, you know, that sort of stuff. So first, we're finding the model. Okay. So I'm going to input this information into my original formula. So I have T equals C, which is 70, plus T sub 0, 450, minus C, which is 70, times e to the kt. So I can simplify this a bit and get 70 plus 450 minus 70 is 380, e to the kt. Now I use my ordered pair in order to solve for this constant k. I need to know what the heck that is. Okay. So I take my ordered pair and input it. So I have 300 for t equals 70 plus 380 e to the k times 5. So I'll have 5k. Right, so I have an exponential equation. I need to isolate this exponential term. So begin by subtracting 70 from both sides, 380 e to the 5k equals 230. And then we'll have 230 over 380, so I'm dividing both sides. So e to the 5k is equal to 23 over 38. Simplifying a little bit. Now I'll take natural logs. I have the isolated term here, so I officially can take natural logs. On the left-hand side, the ln and the e cancel each other. You're just left with 5t. And then finally divide by 5, and you get t is ln of 23 over 38 divided by 5. Okay, so that'll be sort of our growth constant, and we can rewrite the entire equation now, given this information. We'll have t equals 70 plus 380 e to the ln of 23/38 all over 5 times t. Okay. So the book wants to know how long until, this is part C, how long until the temperature is 140 degrees. So maybe that's the lowest you're willing to go before you throw it in the trash. So this is the t value, so you substitute it in for big T here, and then you're solving for little t, the time. Okay, so you need to again isolate the exponential term. Okay, so I'm going to move the 70 over. 70 is 380 e to all this business. Divide both sides by 380. So you have e to the ln of 23/38 all over 5 t, and on this side we'll have 7 over 38. Okay, so I've isolated the exponential. Now take logarithms on both sides. Ln e to the ln of 23/38 all over 5 equals ln of 7 over 38. Then the ln and e, of course, cancel each other. You got ln of 23 over 38 over 5 times t equals ln of 7 over 38. Multiply both sides by reciprocals, so 5 all over ln of 23 over 38. Then times over here 5 all over ln of 23 over 38. And then finally, our t value is 5 ln of 7 over 38 divided by ln of 23 over 38. And you can approximate that as 16.85 minutes. So you don't have a lot of time really to get the pizza out the door.